Hello, my name is Andrew Kucher, and today I'm going to be solving problem 7.18 from Fundamentals of Heat and Mass Transfer by Bergman and Levine. And just for a brief rundown of the question, 7.18 is calculate the average heat transfer coefficient for the plate from problem 7.17 when everything is rotating 90 degrees. So unlike, as you can see with problem 7.7 up here, 7.17 rather is having you do calculate the heat transfer coefficient when air is running over two plates. In the case of this problem, it's going to be both plates perpendicular and in contact with the air. For 7.17, one's in contact with the air first, but in this case, both are in contact with the air at the same time, which makes it easier for us, as in this problem, as you can see from this example here, the air is going to be running over both surfaces, which are both squares. One is rough, the other is smooth. So what we need to do is determine the Reynolds number, particularly for the smooth surface, to determine if it is a mixed case. And we have to use the mixed uh, uh, heat transfer coefficient calculations. So doing the Reynolds number for the length of the surface, it's the speed of the air, which is U infinity, 25 meters per second, times the length of this surface, half a meter, divided by V, which is right below here. V is for the air properties at atmospheric pressure, which is 298 Kelvin, 1 atmosphere. 15.5 times 10 to the negative 6, which gives us a Reynolds number of 806,000. If you look up here, the transition is determined to be at 500,000. So this does transition across the surface. So it is a mixed case for the smooth surface. It's also steady state because nothing's changing with time, constant properties. We don't expect anything to change once we calculate it. There's also the boundary layer being tripped at the edge of the rough plate. This basically just means that it's going to be turbulent the entire length of the plate. Um, So for A being mixed flow, we determine X of C, which is 0.13 times M. And then we use the equation for mixed flow from the book, which I believe is equation number 7.38. So using 7.38, we then just plug in the values that we have for the Reynolds number, Prandtl number, the K of the air, and then the length of the plate. And then we get for the heat transfer coefficient for A, we get 50.683 watts per meter squared Kelvin. The average coefficient, that's what the bar is for. Um, Reynolds number is the REL. In this case, we're not using the 500,000. We're using the value we calculated up here. Prandtl number is from the air properties. Um, and then 871 is calculated A. It's this constant here. This is what makes this the mixed case. And it's using the 500,000, the REXC. So you calculate that out and you get 871. And then once you do that, you get 50.683 watts per meter Kelvin. And then for the rough surface, it's a lot simpler because we don't have any mixed flow. So it's just rough the entire distance. So there's no constant. And it's pretty much the same other than that, though. And then calculating that out, we get the average heat transfer coefficient across surface B as 91. And then for the average for both of them, you literally just add them up and then divide them by 2, the average. And that results in the H bar average being 70.867 watts per meter squared Kelvin. All right. I hope this is helpful. Have a nice day.